of the methods for making nuclear fusion energy is the magnetic confinement method, where atoms are forced together in order to fuse them, creating high amounts of heat energy.
Right now there's two methods that they use. One is called magnetic confinement, where they use huge supermagnets or electromagnets to contain the, well, they're actually going to heat up the deuterium and tritium into the plasma, into a gas, and then that they're going to try to force and heat up by the pressure from the magnetic fields to higher and higher temperatures, and then ram them together, in a chamber that's also magnetically steering this plasma to force them to fuse under really, really high temperatures. Okay, 100 million degrees Celsius. All right, that's one way to do it, because you can't and then once that happens though, it gets so hot that even though you're cooling down those magnets like they're doing in France and in Europe, in Britain, they use that magnetic confinement technique, and the other place too. There's a few that use it, but they can only do it for so long, and then they say, we have to shut it down because it's too hot. We can't. and so there's too much energy there.
The other method, called inertial confinement, utilizes pulse lasers that bombard and heat a pellet so that it fuses and gives off energy.
California, Lawrence Livermore National Labs. There's a place called National Ignition Facility. Okay, and they've been working on fusion for a long time. Okay, but they're doing a little bit different than the magnetic confinement. It's called inertial confinement. Okay, so what they're using is lasers to bombard an element, and so what they do is it's a huge facility. It's like 3 football fields. It's huge.
Wow, is that big? Wow.
So because what you got to do is you have to take this powerful laser, you split it into all different kinds of lasers, and so that you can route all these lasers and come around and hit this container at around like 360 degrees of it bombarding this material of deuterium and tritium. So, and the problem with that is it has to, as you split them and as you route them around in this big facility, and then as you finally ramp them together, it has to be precisely timed so that they all come there at the same time. They had some luck instead of using plasma, they created they put the elements in a tiny pellet, smaller than a BB, and they have it in a little container. What they do is they bombard this container with all these lasers, pulsing it, and heats up the container. The container then creates, as they bombard it, it creates X-ray radiation as well as heat, and then that energy from the heat and the X-rays bombards the pellet, and then the pellet fuses, and then that emits energy. So they did that with one pellet, and they estimated that they put in 2 megajoules of energy from the lasers, and when the pellet fused, they got out over 3 megajoules of energy. Okay, so that's the first time I've ever heard of anywhere in the world that we actually got out more energy than we put in any one single reaction. So that's pretty exciting. Okay, so that's maybe getting closer to solving that problem of getting more energy out. Now they only did it for 1/1000th of a second because it was just one, one BB or something. But that's a step in the right direction, right? So that's kind of.
There are 3 other magnetic confinement types of nuclear fusion reactor sites across Europe and China, which we will discuss.
There's a one in UK where they use the magnetic confinement, and it's called the JET Lab, or the Joint European Torus, and that one, they've been able to run that one they started it back in 1997, and so they had some success. But again, they only ran it for a little bit, and it's less energy that they're getting out than they're putting in. But their big milestone recently was they had it going on for I think 5 seconds, 11 megawatts of power, but then the magnets get too hot. So that's their time. They're doing more time, but they're not getting as much energy out. So they're working on that. Then there's the France one, or the European one. It's called the ITER, or the International Thermonuclear Experimental Reactor, and that's the one they think that would be the closest to being a prototype in the world. And so they're actually working on that fervently. They're hoping to get like a prototype up by 2040. I don't know if they'll make it, but they're working on that. And then there's the one in China. It's the tokamak facility, and so there's a lot of countries working on it, which is kind of interesting. The one we didn't talk about was the Helion 6 reactor. The Trenta facility where they use the HE3. They're the ones that came up with the idea of using HE3. So, and they're also using magnetic confinement. And so, like I said, maybe we can cooperate with each other and try to tackle the confinement and the energy output and the material production all together as we work towards the things. Maybe combined forces would be the most effective solution to get there.
So our message is if in all that problems, you'll go with nuclear energy and help develop fusion power as well.
Well said, brother. Well said.
Yeah.
All right. Let's end there. Well, until next time.
All right.